All right, let's get started, shall we? Couple of items, just quick items. Homework 2 is due next Wednesday, April 7th. I think at midnight is what the homework says. Exam 3 is a week from today in class. All right. Now I won't be here that day because I'm going to be leaving on Wednesday, but the TAs will be here to give the exam like last time. And this is the missing solution that I promised you I would show you today. I had posted it on the board. I don't know why I forgot to do it in class the other day, but it's the last one in Lab 9. The idea here is a perfect number returns true if n is a perfect number, so that's the argument. And the way we do this is simple. We return true if n is equal to the sum of all of the numbers in the range from 1 to n if n modulos 1 is 0. That means that I evenly divides n. Now this is wasteful in a sense. You could do much better. How can I make this faster? Anybody? Do I have to check all the numbers between 1 and n? Go ahead.
I don't think you have to check the numbers that are greater than half of that.
Right, so if I want I to evenly divide n, can I be n minus 1? Obviously not, right? So the best I can hope for is go up to n, sort of the middle of that range, n divided by 2. And so I can tweak this end index here to n divided by 2 and get a shorter range to check, and it'll be faster. But this is fine. It fulfills the requirement. It tells you exactly how this works. If I look at the number 6, for example, which you know is perfect, I'll start with 1, which perfectly divides 6. 1, 2, and 3 all perfectly divide 6, so they will return true here, and they'll be collected, which I'll then sum to get 6 and check against n. And if it doesn't sum to n, it returns false. So I apologize for forgetting to include that. All right, so we were writing the Boggle game, which I hope we can make some progress on today. There are two things I want to talk about as we do this. One I introduced the other day. We talked about printing and the string and the representation version. And so we need to talk about the distinction between these two things. We're going to do that first. And then the other thing we're going to talk about today is exception handling in Python, which has a really nice application in Boggle. So ideally, when I print something like in the REPL, I print it for the user to read it. So if you're interacting with Python and you say, what's 3 plus 4? You expect Python to say 7. That 7 is for you to read. But there's another reason to print something or to see something or to pass back some value, and that is that I might want to capture that value and use it for something. And these two things are distinguished and in fact can be handled separately. So one example of this distinction we've seen before, this is a string. That's a carriage return, \n, a test. And when I type s and evaluate it in the read eval print loop, this is the value of that string. It is simply the string. But if I print s, what happens is this string gets handed to the print engine, which consumes the quotes and consumes the \n, realizing it as a new line. So there's a difference between the value, which is a string, and the printed representation of that value, which is for you to interpret, not for Python to interpret. The advantage of this representation is if I assign s to something like this, I can actually later print it, so I can save it in Python. This print statement here, what is the value returned by print? Anybody remember? What does print return as a value in the read eval print loop? Go ahead. None. Returns none. So there's no value returned here. If I say x equal print s, x will be none. I'll get an error, right? But this is just the printed out version which appears before the value is printed by the read eval print loop. So there are two functions in Python, special built-in function. One is str, which we already know. What have we used str for before? I'm sorry, somebody said I didn't. Right, so this is essentially the constructor for the string class. We've used it as a conversion function. give you something, I convert it to a string. What I'm really doing is I'm creating now we know what's going on. We're creating an object of type string that has a certain representational value, which is the string that we want to create. But there's this other function called repr, or represent, and they have different functions. So string of s, when I take the s that I had before, which was this is a test, and pass it to string, I basically just get a copy of that string. It's a new string constructed that has that string value. But when I type the representation of s, when I ask for the s passed to this representation function, what I get is like one step back to the string. What I get is I get a string, because this is also a string, that when read and evaluated generates the string that I had before. Right, so look at this. Let's look at this string. First of all, it's got two sets of quotes, a double quote and a single quote, which we know are essentially interchangeable. If I were to take this string and print it, what would I get? Well, the outer quotes would disappear, but I would still have the inner quotes. And the extra slash here is an escape to this slash, so this double slash becomes a single slash. So printing the representation of this thing should get me the original string back. So in fact, printing the representation of s gives me, this is \n, a test. So we see that the string function returns a string, whereas the representation function also returns a string, but it's a string that when evaluated gives me the string that I want to have. So it's like one step removed. Does everybody see this? So for objects, in our class hierarchy, we have the same mechanism, except now string and representation become built-in methods. And that's why you see them with the underscores on either side of the name, string, and representation. So these methods are actually part of the original class hierarchy. When you create a new class, define a class, you're going to get default values for these methods. These methods are built in to the class hierarchy. You can, however, we haven't talked much about inheritance, if at all, you can, however, define custom versions for your class, and that's what we're going to do for Boggle. So I'm going to show you how to replace the built-in versions of these for the class that you define. So the two methods have analogous functionality to the two functions we just saw. This particular string method here is, if it's present, it's meant to produce a human-readable form of the object, something that you want to see, so that you, as the user, can interpret what that object is. Now, an object, imagine that we're building a registrar's system for a university, and I'm modeling a student as an object. The printed representation I might like to see for the student object itself is not a dump of all that student's data, but just a last name, comma, first name might be sufficient, so I can identify who the person is. On the other hand, the representation method is supposed to produce something that a machine can read, Python in this case, and presumably reconstruct the object. So it's like you dump something with the representation method, you want to be able to have that property of being able to read it in and reconstruct the object. Have we met that? Have we met that criteria before? Well, I think so, because the representation version of this, when I read that, gives me back, when I read and evaluate that, gives me back the original object. So it has the same functionality. Okay. Now the other thing you should know is that in the original class hierarchy, if you don't have this method defined for your class, but you do have this method, then this method is used for both the repr and the string. So they are the same. You only need one of them. You only need one of them if you're satisfied that everything that you print will be like a dump of that object, so you can see everything associated with it. Now in this particular application for Boggle, we want to separate these two things. We're going to actually implement only the string one for now, and then later we're going to build a representation one. And here's my thinking. The string one is the one that I want to see when I evaluate that Boggle object in the read eval print loop. And since we're playing the game Boggle, it seems to me that the string method should produce a nice 4x4 character grid of the letters in the Boggle puzzle. That's what I care about as the user. On the other hand, one might envision, and we'll do this next week, that if I'm playing the game of Boggle and it's time for dinner or something, I might want to just save that game and restart it later. And so I could use this method to print a version of the game that contains all of the internal information, including whatever words I may have already found, whatever guesses I may have already made, whatever other statistics I might be keeping. Anything and everything to do with the game could be printed out in such a way that when I read it back in, I get the same Boggle object in the same place where I was. That would be kind of cool. Okay? So that's the plan. We'll see if we get this far, but we're certainly going to get this far today. So here's my string method for Boggle. So this is a method inside that class definition. And you'll see that, oh nuts, this 0 is not there. This is the null string. I apologize. When I copy to my slides software from Python, some escape characters get turned into nulls, which appear as zeros in my slide. So here, let's just look at the real code. You can see this, right? So here, as you see, the character that caused the problem is the \n. So this is my code for printing out the game. And we have to sort of remember what the game looks like. We haven't quite seen the game representation yet, but I will tell you that it is a list of lists kind of representation. And what I have here is inside here I have row column in the board. So the board is represented as like a list of lists. And I'm going to print out the letter that's at row column position in the board in uppercase for every column from 0 to 4. So I'm going to step through all the columns. I'm going to print out the letters. And the outside part of that is I'm going to step through the rows from 0 to 3. And I'm going to join each row together with a new line. So I join the rows with a new line, and I join the columns with just a space, just a blank. Actually, that's a space, so that I get the letters printed out. So let's see how that looks. I'll run this, I think. So this is what that part actually looks like. That is that's what I get when I print Boggle. Let's just try this again. B is my Boggle board. No, B equals Boggle. So I'll create Boggle board. I'm going to quit. I really hate Windows. I really do. Okay. So if I look at the Boggle board, and I type B, what am I actually seeing here when I type B? So B was set to an object of type Boggle. You can ignore all this stuff that happened. This is when I type B and evaluate it, what I get here is the output of the representation method, the REPR method. And it's hardly human readable. It just tells me that this is an object of type Boggle, and this is the memory location where it's stored. But I couldn't possibly read this into Python and reconstruct the state of the board. But if I print B, now I'm going to get the string version of that board, the str method version. And you can see that printing it gives me a printed representation of the board that's constructed by doing each row one at a time with a new line and joining them. So there's a new line here, a new line here, and a new line here. And then each letter in each column with a space between them. And I apologize for the fonts here. They're not fixed width fonts. These are variable length fonts. So they don't quite align. We'd have to pick a better font to make them line up one over the other. All right, so does everybody get the idea of the representation string and the print string? Any questions? All right, the next step in our game creation, we want to create a particular instance of the Boggle game. So when I create this new Boggle object, one of the things I have to do is shake those special Boggle dice, those special 16 dice with the characters on them, to get a particular puzzle instance, a grid of characters. So this is actually pretty straightforward. I'm going to create a new method called newGame. And you'll see that I'm using a function here called sample, which comes from the random package. So the sample function takes a list or a sequence and a number. And what it does is it generates a sequence of elements drawn from L without replacement. So let's talk about sampling or drawing from a hat. If I have a hat full of colored marbles and I ask you to pick a marble, let's say all the marbles are different color, there are two ways you could go about this. You could just reach in and grab a marble, say you get the red one, and then I ask you to pick another marble. You could throw the red marble back in the hat and draw again at random. So this is called sampling with replacement. And what that means is after I sample a marble, I throw it back in the pool so it could be picked again. And this way you can sort of imagine sampling a bunch of elements from a set, one after the other, after the other, after the other, and there might be duplicates because you might pick the same thing twice. This is essentially what randint does. If I have a list of a certain number of elements, and I invoke randint on 0 and the length of that list -1, I'm getting a random index into my list. If I invoke it again, I'll get a different random index. And I keep doing this, I may eventually get the same random index, right? You might generate it twice. So that's sampling with replacement. What sample does is it samples without replacement. That means if you start of a list of 10 elements, the most elements you can sample from that list are all 10 of them. And what sample does is it picks them out in random order. But because it doesn't replace them after it picks them, that the sort of number of choices you get as you keep sampling gets smaller and smaller until when there's only one marble left, that's the one you're going to get. So here we use sampling. Why? Because what I want to do is I want to make sure that I get one face from a particular dice. Remember that the die here is a 6-element string that has the characters on the 6 faces of the die. Sampling that string for 1 will give me one element of that dice, one face. So this is like roll 1 die, you get 1 face. The 0 means because the sample here will give me back a list of elements, one after the other. It'll be a list of length 1 with the first character, and I want that first character. So this will be my first dice, the first letter from that dice. But notice, each die is sampled without replacement from the set of die D. We saw this the other day. The D set is the list of all the dice as strings. Let me show you that again. Here is the D list, which has all 16 die in the Boggle game, where each face of the die is one of these letters. So when I sample this thing 16 times, I'm essentially getting all 16 dice in some random order. Because the order in which I draw the dice tells me how they populate on the grid. And in generating a new Boggle game, there are 2 sources of randomness. First of all, which face does a particular die show? Which face is up? And the second one is, what order do the die appear in the board? And so I'm handling this in newGame. I'm handling a newGame with this comprehension. I'm sampling the die to get them in order, and then for each dice I'm sampling them to get one face. And that gives me a list of 16 characters, one for each position on the board. And I'm going to set the board, which is part of my object, I'm going to set the board local variable self to this list of lists. I'm going to partition the game, 16-element game list into the first 4 as the first row, second row, third row, and last row. And now that you see how the board is set up, you can understand how that string representation print worked, where I iterated over the board to get each row, and then I iterated over the row to get each column. So when I when I type print B, if B is of type Boggle, this is the underlying data structure that gets printed by that string method. Okay? Everybody with me so far? Yes? All right, so here is my self.board constructed. So I now have a new board set up. And I'm pretty much ready now to play the game. I've left some details out, which we're going to pick up later. You'll notice that of the original variables in the board object, in the Boggle object, I have all the legal words read in. I've initialized my board. Sure, I've set the cheat mode, but I haven't actually done this find all solutions. So to play Boggle, I have a couple of strategies to build this game. One is I could just do what I've done so far, build the board, and now turn my attention to building an interface that you can actually navigate on the boards to spell words. All right? And once you spell a word and say, here's a word I found, I have to check somehow two things. First of all, I have to check that the word you found is, in fact, in the legal word list, so that you can't spell BRZKK and say that's a word and it should count. It's not a word. It has to be a legal word from the English dictionary we're using. And I can do that once you type in the word and I interpret what it is on the grid. I can check to see that it's in my red words, in my legal word list. Sorry. The second thing I have to do is I have to check that the path that you gave me to spell that word it does spell that word. In other words, that it's a legal path that goes from one location to the next that's adjacent, and it navigates that 4x4 grid, and so I can spell the word that you want me to spell. Now that part is easy because you're going to somehow tell me which characters on the board, and as you type them in, I can see if it meets the rules of what a legal path should be. But the extraction of the word then is fairly straightforward, and checking against the read words is really pretty straightforward too. But the one thing that's missing here is I have no idea how many words are actually present in this roll of the board. Because I'd like to somehow give you a score. I'd like to say, yes, you have identified 12% of all the words that are legal. And so to do that, I need to take one more step. And that one more step is I have to have my program actually solve this particular instance of the puzzle. So when I roll the board and I have a new board, I need my code to find every legal word that's embedded in that board. And the reason that I do that is so I can tell you there are 47 solutions in this board, and you need to find all 47. But it also makes the process of checking whether the word you spell is a legal word easier, because instead of checking it in this huge list of words, I'm just going to check it in the list of words that I know exist in the grid, which is a much smaller set. Now, to do that, we're going to have to do a little bit of extra work. And I'm going to leave it aside for now. Instead, what I'm going to do is I'm going to focus on this last method. So we've already seen read words. We've just seen new game, although we didn't see all of it. I'm going to skip self.solve, and I'm going to focus on self.play, which is the function that sort of governs the flow of the game, that interacts with the user, that lets you type a path, and so on. And I will then later wrap back and look at self.solve and finish new game so that we have all the hooks in place to check that the words that you type in are actually legal words. So let's see how this looks. So the play method should do two things. It should, remember, we've just created a Boggle object. We've just created the board, the puzzle that we want, the puzzle instance. This play method should manage the play of this puzzle, and then it should manage the interaction with the user. So the user, when they're done with this puzzle, should be able to say, okay, I'm done with the game, or maybe say, I'd like a new puzzle. I'd like to change puzzles. So we have to sort of manage this interface with the user, not just at the level of typing in the path of the word that they're picking over and over and over again for all the words that they find, but also things like, I quit, or I want to play a new game, or show me the board again. So We'll do that here in our play method. Print out a little banner. And then you'll notice that there's an infinite loop here. And what the infinite loop does is it invokes this self.round method, which manages the play of one puzzle instance. And while this thing returns true, we will generate a new game, solve it, and then play the new game. So this is our generate a puzzle, solve it, play it loop. And we're going to keep doing this over and over and over again. Now notice we're starting kind of out of cycle because the Boggle constructor created a new game and solved it itself. So we have already done, when we create the Boggle object, we already have a game picked out and we've already solved it. So we can start by getting the user to play it. But then as the user plays the game, if they exit round by returning true, they get a new puzzle. But if they exit round by returning false, then the game is finished. And because self.round is false, it'll just print thanks, stop playing, and we'll be done. Does everybody get the gist of the management of the game? So we divide the game up into a bunch of sort of episodes, and each episode is the play of one game board, which ends with either the user giving it up, solving it entirely, or being done with the game in its entirety and saying, I quit, I'm done. So what happens here? The round method manages the user interaction. We're going to replace this method later with a mouse and point and click kind of method definition. We're going to do it so we can play the game live with a mouse. But for now, we're just going to let you type in the path of the word you like. So each invocation of this round plays a complete puzzle and then returns a Boolean saying whether you want to go on or not. And our path through the puzzle, for each word, I'm going to let you type x, y integer coordinates. Just for a path of length 4, you're going to type 8 integers on the line. Those are the x, y, x, y, x, y, x, y. And then there are also some other characters that we're going to accept. We're going to accept the slash as shorthand for saying, show me the puzzle. I want to see it again. We'll accept colon to show me how many words have I guessed so far. What are the words I've already found? And we're going to let plus be generate a new puzzle. And finally, missing here, my bad, we're going to accept period as I quit. Now to get this function sort of configured, we're going to need one additional construct that we mentioned briefly in class, and I told you we'd get back to it. And that's the topic for today. This is an important topic that you need to know how to use in your code. And the topic is exception handling, try except. So we've already encountered errors in Python. You've certainly encountered your share as you write your code. Usually what this means is that you'll be running a function you write and Python will say, there's a divide by 0, I break. And you'll get a little error message and you'll be popped up to the read eval print loop and your code is broken. Well, wouldn't it be easy, wouldn't it be neat if I could take advantage of this detection of an error in such a way that when an error occurred, if it's an error I expect, I can catch that error and take corrective action. And that's the whole point behind these try except clauses. So let's take a look at this. Let's assume that I was reading, and this is from an old assignment, so we have a different comma separated value file. Let's assume that in your homework assignment, you're reading in, let's see, you get in a time and date, you get a student identifier. Let's assume that the student identifier that you read in your data file has an error in it, and one of the digits has been changed to be an integer, a character like A. Now, I don't know about you, but in my solution, when I read in the student identifier, I turn it into an integer. Right? I represent it as an integer, not as a string. So if I try to represent that as an integer, I will get an error because A doesn't have an integer representation. So if I just simply tried to do int on this, Python would give me an error. And this is the same kind of thing you normally see. You see the type of error here, the value error, and then there's a built-in error message. It tells me what the value is and why I can't turn it into an integer. And when this happens, we say that Python throws an error. So what we'd like to do is really literally catch this error and correct it before we go on. So here's how we can do this. We're going to try this convert if you can function definition. It takes a string, and what it does is it tries to return the string, the integer value of that string. So you'll notice that the only thing that's different about convert to int if you can is that we have this try colon except colon. And what this does is, when you get to a try except, the evaluation order turns immediately to evaluating the code in the try. And if this code works perfectly, it's as if the try and the except didn't exist. So if string were the number 1000 as a string, returning int 1000 would simply return 1000 as an integer. But if the string was 1000a, which cannot be converted to an int, the stuff inside the try, while Python's evaluating stuff inside the try, it will throw an error, as we just saw. But instead of having that error interrupt execution, because it's inside the try except, what Python will do is say, oh, this part returned an error, so I'm going to execute the part here in the except. So the stuff that I catch as I execute the try, any error will go to my except element, my except clause, and start executing from there. So see what our try convert to int if you can function does, is if it can't convert it to an integer, it prints out a message so at least I know it failed, and then it returns an integer that presumably is a code that doesn't make any sense to me. So if these were in fact dates, years, the year 9999 isn't really relevant to me. Maybe it would return a -1 instead. Doesn't matter. But it returns an integer that I can detect means the integer that I gave it wasn't an integer, couldn't be converted. So for example, convert to int if you can, because this string can be converted to integer, simply returns that integer. But if I add the a to it, what happens is I get the printout here, whatever is here gets evaluated, and the value that returned is the value I substitute for it. This is a very handy construct. In the AutoGrader, we use try except all over the place because I don't know when your code's going to break, so I have to catch those errors so I don't have to manually edit your code to correct them every time. I catch the error and subtract the credit for the function that broke. That's how the AutoGrader basically works. Now, I can actually do some little bit more elegant things with try and except. You remember that the errors that you get don't always have the same message. In fact, when you get an error in Python, it always tells you not just the message here, but it also gives you a type of the error. This is a value error because I can't convert that value to integer. We've seen other errors before too, and the cool thing about try and except is I can actually decide which kind of error I want to capture with each exception clause. So instead of just a try and an except for any exception clause, think of it like an if, else kind of construct. I can have one try with a bunch of exception clauses where each exception clause is tuned to a different type of error. And then I can have the final exception clause that doesn't specify an error type that catches all of the remaining types of errors. So here is my new convert to integer if you can. If the try works, it's absolutely fine. I'm going to simply return the integer. If there's an evaluating here throws a value error, I'm going to catch that error in this exception, and I'm going to print out a better message that says, not really an integer. And then I'm going to return 9999. And if there's any other error, an error that is not a value error, but is some other kind of error, I'm going to catch it with this sort of like the else, and I'm going to print out the value, unexpected error, and return a different code. Do you see how this could be useful? All right, so that is the gist of the try except. Now we were going to use try and except to build the round function. And so I'm going to switch to our code here. Oops. And we're going to look at the code for round. Now, I couldn't put this on a slide because it gets long and messy, but and I will give you this code eventually when we're done so you can play Boggle. But this is my round method, which will eventually be replaced by an interactive version. It's actually pretty straightforward, but you'll notice the first thing we have here is a built-in helper function. Now, I told you before that, and I think I think I showed you how the game plays before. When I want to specify a word, a path through the puzzle, I'm going to give you a series of x, y coordinates, all integers, all on the same line, all separated by spaces. I'm not going to ask you to print left parentheses x comma y, right parentheses comma, left parentheses x comma y, right parentheses, and so on, because that's tedious. I'm just going to let you give me x, y, x, y, x, y, and so on. But of course, inside the game, I need to interpret those x, y values as pairs of values. And in fact, I'm going to represent the path that you give me as a list of tuples, where each tuple is an xy pair. And what this little recovery function does is it takes a path, which is just a string like this, and converts it to a list of tuples. How do we do it? Well, obvious thing, I'm building new structure. I'm going to use a comprehension. First thing I'm going to do is I take this path, which is a string, and what I'm going to do is I'm going to split that path up with the spaces as the split to get a series of single integer strings. And I'm going to invoke integer of v for every v in that path and collect it into a new string. Could have used the map function. I chose to use a comprehension because I think that way. Now I have a path that is not a string of integers, but is in fact a list of integers. And what I want to do is I want to convert it from a flat list of integers into a list that looks like this. I'm going to return that comprehension where I have a tuple for path I and path I plus 1. And I will simply let I range starting from 0 and going up to the length of the path, but by 2. So I'm going to skip every other element. And that way I can index path I and path I plus 1 to get my path back. So this little recovery function is just a helper function that lets me see the string that you type in, the string of integers, as a list of tuples of integers, which I can then use to recover the word from the puzzle. Are we clear on this? I only use this in the user interface, so it's a helper function of the round method, because I don't need to use it anywhere else. So why make it a full order method of the class? Let's just hide it away where it belongs. All right, so that's my definition. The next thing I do is I print out some simple instructions. This is what the user will see. They'll see a little input, row 1, column 1, row 2, column 2, or type slash for display, or show, colon for show, or plus for new puzzle, or period for quit. And then where R1 specifies a path of a series of row column coordinates. So this is the instructions I give the user. Terse, but it's better than nothing. I also create a list, an empty list of words that I found. I print myself. Notice that printing myself invokes the str method that I've previously defined. So this is actually what shows me the board. And if self.cheat is true, I'm going to print the solutions that I found for this board. I haven't shown you that part yet, but assume that the solutions of this puzzle are now embedded in the solutions variable. So if my cheating bit is on, I can actually see what the solutions are before I actually try to play the game. All right, then I have this loop, which is while true, so it loops forever. And that means that the only way out of this loop is if the user presses a key that causes the loop to exit, to break. So it's a loop. The idiom here is loop forever until somebody tells you to stop. And that is the heart of the interaction with the game. So let's just bring it all up here. Here we go. While true. I'm going to print out my Boggle prompt, and I'm going to invoke the input function on it. Or the input function, have we seen input before? I think we have. Yes? So the input function takes a string that it prints, that's the string it prints, and then returns whatever text you type to that prompt. So it gives me a prompt, I type some characters, hit enter. This input will return the string that I just typed. But notice what I do to it. Before I recover it as a path, I'm going to strip that string, which removes any extra white space characters on either end, including the new line that's at the end of that string. And then I'm going to cause it to go to lowercase. So I've turned my whatever you type into some canonical string of lowercase characters separated by spaces. I check if that path is the slash mark, because that's my way of saying show me the display again. If it is, I just print myself and invoke continue, which you recall goes back to the beginning of the loop again and prompts me again. Otherwise, if the path I give you is a colon, that's show me the words I found so far, I'm going to print this out. Here are the words. I found so many of these words so far, and I'm going to sort them and I'm going to print them out. And then I'm going to go back to the beginning of the loop. If what you give me is either a period or a plus, path in either one of these characters. Remember, the plus says, give me a new game, and the period says, I quit. So the plus here, either one of these things will cause me to print out a message that says, you found 17 of the 47 possible words. And then depending on whether the path given was the plus, which means play a new game, or a period, which means I quit, I will return either true or false, so that round will go back again and generate a new puzzle, or will quit and be done. And finally, here's my try except. What the try except does is it tries to recover the path from the path that you printed. So give me the list of tuples. And then I'm going to use this other method, which you have yet to see, and say if the word that's extracted along this path is already in my word list, that means I've already found it. So I'm just going to say, hey, you've already found this word. Otherwise, I'm going to add that word to my word list as a word that I found, or so this is my if I get a path back, if this path is a legal path, I'm going to handle it this way. If the path is not a legal path, I'm going to say, I don't recognize this word. It's not a legal word in my dictionary. And if anything goes wrong in here, I'm just going to give an error and say, this is improper input. It's at the end of the loop, and I'll go back and do it again. So all of this should be easy to understand, a small thing at a time, but when you put it together, you actually get a fairly usable user interface. Oh, come on. Oops. Oh, sorry. So I load it into Python, creates a new object. It tells me what the legal solutions are. My cheat bit is on, so it shows me that in this puzzle there are only these three words, the only words that are legal that occur in the puzzle. There's my opening banner and my instructions to the user. And so let's see what words I have. I have W-O-O-F, so this is 0, 0. So it's 0, 0. Then I got to go to 1, 0, and then I need to go to 0, 1, and the row is 1, 2. Oh, sorry. The word that I have is woofs. Where's the S? Yeah. 0, 1, 0, 0, 1, 1, 2, and then that's 1, 1. Yeah, remember the word list that we're using is the one from WordNet. They're all 5-character words. That's why woof is not there. All of the words in this puzzle will be 5-character words. So when I typed the string in, I got the tuple 0, 0, that's that, 1, 0, which is that 0, 0, 1, which is that O, 1, 2, which is that F, and 1, 1, which is that S. And so it reconstructs the word woofs, and I get that added to the list. If I hit the colon, it will show me the words I found so far. If I hit the slash, it'll print out the puzzle for me again. If I hit the plus sign, It should tell me how many words I found of the possible words, and then it should generate a new puzzle, which is what it does. This puzzle has if you don't use an operating system very often, it's very hard to remember what the keyboard shortcuts are. So when I hit the plus sign, it tells me how many words I found, creates a new solution, a new game. The cheat bit shows me what the words are, gives me the input again, and presents a new puzzle, and I'm off to the races. If I hit the period, no, that wasn't the period. If I hit the period, it says you found 0 of 10 possible words and exits the game naturally. Everybody get it? So we're going to stop here. On Monday, we're going to do the solution, solving the puzzle to find the legal words. And that's going to take the whole hour because it's a search process. In fact, you will recognize it's very much like WordNet in some ways. So we're going to find all possible solutions of words in that puzzle, and then we'll be done with Boggle, and we can go on to the user interface. Have a great weekend. I'll try to keep up with your questions on homework 2, and good luck.